Good afternoon, everybody. Thanks for the introduction. My name is Cecilia Occhiuzzi. I'm from the University of Rome, Tor Vergata. And today I will discuss with you the design and the early results of our NFC system for 4-channel electrochemical sensing of body fluids. The area of my work is point of care, that everybody knows as the site, as the device that give us the possibility to take care of the patients in different place and in different conditions. There is an increasing trend, a very recent increasing trend, about the possibility to exploit IoT technologies for point of cares. So what I mean is that there is an interest in using for point of care analysis also our smartphone to follow also with the electrochemical sensor low-cost approach and sharing information. In order to put together all these requirements, one of the possible solutions is to exploit NFC RFID technology. Everybody knows what is an NFC, that is the contactless method that we use with our smartphone. No? Okay, when we tap our smartphone on a card on payment site, well, it's possible to exploit NFC RFID in order to perform some electrochemical biosensing using smartphone as a reader and safely transmit data through architecture that take into account also privacy and data security. This is one of the different examples that is possible to find in literature. In this paper, we demonstrate that it's possible to use an NFC, so a battery-less, wireless, low-cost solution for performing, for example, the analysis of our sweat by using a kind of epidermal antenna that is placed over our skin. So these are other examples in which it's possible to demonstrate that we can use this technology for measuring the pH, electrolyte, temperature, and many other parameters of our sweat. Well, so it's well assessed that there are some NFC IC that can act as potentiostats, so they can perform different techniques of electrochemistry, so amperometric, voltammetric, cyclic impedantiometry, and so on and so forth. But one of the problem related with this device is that they can only sense one single analyte per time. So what if multi-analyte sensing is needed? That is very common in our field. Well, the aim of this work is to design a multi-analyte sensing system that can work for now off-body, so we will design a board capable to contemporarily analyze up to 4 analytes in biological liquids. So today I will present you the early stage of this research, so the design of a multi-chip NFC board and the design of a 4-channel microfluidics. The components of the system are this one. They have been already published in other papers, so we can have an ad hoc screen-printed sensing electrode, 4 electrodes. So a classic one with a working electrode, a counter electrode, and a pseudo-reference electrode. Then we will modify what we already studied about a paper-based microfluidics, so with drop place, a channel and a waste place. And then we will use this IC, that is the 4343 by, I don't remember the name, I will give you at the end, SIC 4343, that is an IC that allows us to perform different electrochemical measurements. And our final goal is to create an object more or less like this. So since this is the first attempt, we will use the demo board of the NFC. So for now, we won't design a new NFC antenna, a new NFC circuit, we will use the demo board, and we will focus the attention in the arrangement of this antenna and in the design of the microfluidic, because it's extremely related to the NFC sampling of the sample, because we have to use the same drop of fluid, spread it uniformly on the different channels, and also assure that the timing in which this drop is spread is in line with the interrogation modality. So we first of all try to use this arrangement of the antenna, in which in blue you will find the microfluidic part with the absorption pad, the waste, and the channel. Then in red you have the sensors, and the rectangular in white are the board. The first problem is understand if it's possible to read each board with the conventional smartphone without interfering with the other one, because NFC chemical sensors are very sensitive to the amount of power they receive. So it's important that we arrange the board in order to have a uniform coverage reading area for each tag. So we use instruments that allow us to sample the electromagnetic fields between the smartphone and the board, and here you have the reading map. As you can see, every board, as expected, has a strong interaction with the reader only in the central part, where the antenna is located with a small area, overlapping area. So we don't expect a strong electromagnetic interference between the circuit. Furthermore, the field distribution is pretty stable, so this will assure that every sensors will be powered with the same amount of power, so non-linearity will be hopefully avoided. Then we design the microfluidic. As you can see from the first picture, we have again the same scheme of microfluidic. So the input pad that is unique because we want to put a single drop of our body fluid at the center. Then it spread up to arrive to the sensing pad in which we will put our sensor. And then, since hopefully this system will be also moved to an on-skin application, we also designed the wasting pad, whose aim is to catch the fluid in order to give to the board the possibility to continuously analyze new fluid from the body, okay? For now, it's off-body, the system, and as you can see from the picture on the right, there is, more or less in 20 seconds, a good and uniform spread of the fluid around the paper that can assure that every sensor should have the same amount of analyte. Then we create this case in 3D printing in order to have something that can be easily portable and easily accessed by several users. And we left open only the central part where we have to put the drop, and instead the electronic circuit and the antenna are covered by the plastic case because we don't need it. And we start calibrating the system. So we tested for this calibration a sensor one by one, so separately the sodium, potassium, calcium, and pH. Sorry, there is a mistake. And we perform regression in order to have the slope and the air parameter of each analyte. And it seems that by considering the standard deviation, the results seems to be in line with what expected. Then we start some tests by using liquids emulating the human sweat. And as you can see, there is a pretty linear behavior of the sensors. We have some problems, still problem with the potassium and calcium, because the sensitivity seems extremely slow, but still the presence of a linear behavior assures us that at least the electromagnetic part of the device correctly responds to our expectation. So these are the early results in the design of this 4-channel device. It seems that the communication performance are in line with the expectation in terms of powering up the sensors, perform sensing activity, and avoid electromagnetic interference among boards. And the calibration also gave us good results in terms of stability and linearity. Now, we have, this is only the starting point, because we have a pipeline of additional work that we have to do. Probably the most ambitious is the test with blood. My colleague in physics, chemistry colleague, are working on modifying the paper microfluidics for receiving the blood, so for allowing the spreading of the blood uniformly on the channels. And we are already started with some tests on some oncologic patient together with the General Hospital of our university. But from my side, so from the electronic side, what we need is to miniaturize this device, because this device can be useful for domestic analysis, because probably it doesn't matter how big is the device I want to use, because I can put it on the desk. It is without battery, so it can last forever. I have only to replace the sensors, but we want to put this on the skin, on the human body, in order, for example, to perform multi-analysis of the sweat. And for sure, it's possible to use this architecture. We have to miniaturize it. Thank you very much. This work has been partially funded by PNNR European funding and under the Next Generation EU European project. Thank you very much.